Welcome to Limelight Engineering. In this video, we will be discussing the groundbreaking discovery made by the Brookhaven National Laboratory of the U.S. Department of Energy, DOE, using autonomous approaches powered by artificial intelligence. Let's get into the video. The Brookhaven National Laboratory of the U.S. Department of Energy, DOE, has successfully proved that autonomous approaches can find novel materials. The approach powered by artificial intelligence, AI, resulted in the discovery of 3 novel nanostructures, including a nanoscale ladder, for the first time. The study was published in the Journal of Science Advances. The newly found structures were generated by a process known as self-assembly, where the molecules of a substance rearrange themselves into distinct patterns. Scientists at the Center for Functional Nanomaterials, CFN, in Brookhaven are specialists at regulating the self-assembly process, creating blueprints for materials to create appropriate patterns for use in microelectronics, catalysis, and other fields. Their invention of the nanoscale ladder and other novel structures expands the range of applications for self-assembly. Self-assembly can be employed as a technology for nanopatterning, which drives advancements in microelectronics and computer hardware, according to Gregory Dork, a co-author. These technologies are continually striving for improved resolution through the use of smaller nanopatterns. Self-assembling materials can produce extremely tiny and precisely regulated features, but they do not necessarily adhere to the rules that are established for, say, circuits. By controlling self-assembly with a template, we may create more useful patterns. CFN, a DOE Office of Science user facility, aims to construct a library of self-assembled nanopattern types in order to expand their uses. In prior research, it was proved that combining 2 self-assembling materials enables the creation of novel designs. Kevin Yeager, leader of the CFN group and co-author, remarked, "It's incredible that we can now design a ladder structure, which no one ever imagined before." Traditional self-assembly is limited to the formation of very basic structures, such as cylinders, sheets, and spheres. However, by combining 2 materials and employing the proper chemical grading, we have discovered that whole new structures are feasible. The combination of self-assembling materials has allowed CFN scientists to discover novel structures, but it has also introduced new obstacles. With many more options to control in the self-assembly process, it is a race against time to identify the optimal combination of parameters to generate new and useful structures. To expedite their study, CFN scientists utilized a newly developed AI capability, autonomous experimentation. In partnership with the DOE's Lawrence Berkeley National Laboratory's Center for Advanced Mathematics for Energy Research Applications, CAMERA, Brookhaven researchers at CFN and the National Synchrotron Light Source II, NSLS-II, a DOE Office of Science user facility annex, have been developing an AI framework that can autonomously define and execute all the steps of an experiment. CAMERA's GP-CAM algorithm powers the autonomous decision-making of the framework. The most recent research is the team's first effective demonstration of the algorithm's capacity to identify novel materials. GP-CAM is a versatile algorithm and software for autonomous experimentation, said Marcus Nowak, a Berkeley lab researcher and co-author. It was utilized ingeniously in this work to autonomously examine the model's many aspects. With the assistance of our Berkeley lab colleagues, we had this software and technology ready to go, and now we've successfully utilized it to discover new materials, Yeager explained. We now know enough about autonomous science to be able to transform a materials problem into an autonomous challenge with relative ease. In order to speed the identification of novel materials using their new algorithm, the researchers created a complicated sample with a variety of features for investigation. The sample was manufactured utilizing the CFN nanofabrication facility, and the self-assembly was conducted in the CFN material synthesis facility. An old-fashioned method of conducting material science is to synthesize a sample, measure it, learn from it, and then produce another sample and repeat the process, Yeager explained. Instead, we created a sample with a gradient for each parameter of interest. This single specimen is therefore a wide assortment of several unique material forms. The scientists next transported the sample to NSLS-II, which generates ultrabright X-rays for material structure analysis. Soft Matter Interfaces, SMI, Beamline is one of 3 experimental stations operated by CFN in collaboration with NSLS-II, of which one was employed for this investigation. One of the benefits of the SMI beamline is its capacity to concentrate the X-ray beam on the sample to a resolution of microns, explained NSLS-II scientist and co-author Masa Fukuto. By studying how these microbeam X-rays are dispersed by the material, we may determine the local structure of the material at the lit location. Multiple measurements at various locations can then illustrate how the local structure differs across the gradient sample. In this study, we let an AI system choose on the fly where to measure next in order to optimize the value of each measurement. As the sample was being measured at the SMI beamline, the algorithm constructed, without human involvement, a model of the material's complex and varied structures. The model was revised after each X-ray measurement, making each measurement more insightful and precise. In a matter of hours, the algorithm selected 3 significant regions of the complicated sample for CFN researchers to examine in further detail. They used the CFN electron microscopy equipment to study these crucial regions in great detail, revealing, among other unique characteristics, the rails and rungs of a nanoscale ladder. The duration of the entire experiment was around 6 hours. Researchers believe that it would have taken them around 1 month to achieve this discovery using conventional techniques. Yeager stated, "Autonomous approaches can significantly expedite discovery. Essentially, we are tightening the typical scientific discovery loop in order to cycle between hypotheses and observations more rapidly. However, autonomous approaches expand the area of what we may research, allowing us to tackle more difficult scientific topics. Moving forward, we would like to examine the intricate interaction between numerous aspects. Using the CFN computer cluster, we did simulations that not only confirmed our experimental results, but also revealed that other characteristics, such as film thickness, can also play a significant influence," Dork explained. The team is actively extending its autonomous research strategy to even more difficult self-assembly and other material discovery issues, as well as to new groups of materials. Autonomous discovery approaches are versatile and applicable to the majority of research issues. We are now deploying these approaches to the large community of users that undertake research at CFN and NSLS-II, Yeager stated. Anyone may collaborate with us to expedite their materials research. In the future years, we anticipate a plethora of new discoveries, notably in national priority sectors such as renewable energy and microelectronics. Subscribe to the Limelight Engineering channel and hit the notification icon to receive more videos. Thank you for watching.